Welcome to Structural Design Spreadsheets. This video tutorial will discuss the design of combined and strap foundations using the CSF version 1.0 spreadsheet. Isolated spread footing is the most common type of foundation and is also the most economical. Typically, columns are centered on column footings, but in conditions where columns are located directly adjacent to the property line, the column footings may be offset so that they do not encroach onto the adjacent property. This results in an eccentric load on a portion of the footing, causing it to tilt to one side. In this case, the use of either combined or strap footings is very effective. The strap beam restrains the tendency of the footing to overturn by connecting it to nearby footing. Design example number 1. Design a combined footing to support two columns spaced at a distance of 6 meters center to center as shown. Column A carries a dead load of 500 kilonewtons and a live load of 300 kilonewtons. Column B carries a dead load of 700 kilonewtons and a live load of 500 kilonewtons. Both columns are 500 by 500 millimeters in size. Concrete compressive strength is 28 megapascals and all rebars are grade 60. According to soil investigation, an allowable bearing capacity of 150 kilopascals can be utilized at a depth of 1.5 meters below ground. Now using the CSF spreadsheet, click on the Footing Properties button to modify the footing configuration. Select footing type to be combined. Embedment depth is 1.5 meters. Assume a 600 mm footing thickness. Concrete strength is 28 MPa. Concrete unit weight is 24 kilonewtons per cubic meters. Set both columns 1 and 2 to be 500 by 500 mm. Set column spacings to be 6 meters. The left side is an edge column and the other is an interior column. Now let's assume a 2.5 meter width combined footing. Also assume the cantilever's length is half the footing's width. Note that the dimensions at first are all assumptions. After we run the analysis, we will see if we have to increase or decrease the initial dimensions based on the load demands. Now we have to apply the column loads. Click on the Generate Loadings Manually button. Notice that there are 8 different load cases available for selections. Cases are dead load, superimposed dead load, live load, roof live load, wind load, earthquake load, fluid pressure, and hydrostatic pressure. These cases are being used by the program to automatically generate loading combinations based on the combinations provided by ASCE and NSCP 2015. In this case, we will use only dead load case and live load case. Apply the given loads to columns 1 and 2. After specifying the loads, click on the Auto Generate Loading Combinations button. Now, loading combinations are automatically generated. Click on the Apply to Structure button to use the generated loadings. Since we are only designing the footing for gravity loads, we only need one combination in service level for footing sizing, and one combination for ultimate load level for use in the design. We can delete the other redundant combos. Please note that the program needs at least one loading combination for service level and at least one for strength level. Always review the applied loads in the structure to make sure it was applied correctly. Modify the soil properties by clicking on the Soil Properties button. Soil unit weight is 18 kilonewtons per cubic meters and it has a bearing capacity of 150 kilopascals. Modify the reinforcement settings by clicking on the Reinforcement button. Set the rebar material to 415 MPa. Now, the footing is ready for analysis. Click Run Analysis button to perform the analysis. After analysis, warning messages will pop up to give you a brief summary of the analysis results. We can see here that column 1 fails in punching shear with a DC ratio 1.036, a bit higher than the limit. Also, the footing fails in one-way or wide beam shear. The program suggests to increase the footing thickness. We can also see that the maximum soil pressure, which is around 146 kPa, do not exceeds our allowable pressure of 150 kPa. This means that our assumed footing size is adequate to utilize the possible soil stresses. However, it can be seen that the soil pressure in service dead load plus live load is trapezoidal. It is advised that for this load case, the soil pressure should be made uniform as possible. This is to minimize the effect of differential settlement between the two columns. We can go back to our inputs and make the necessary modification to satisfy the serviceability and design requirements. Let's increase the footing thickness to 650 mm to satisfy the shear demand. Increase the cantilever length to achieve the uniformly distributed soil pressure. Click OK to save our modification. Now, perform the analysis again. This time, no warning messages popped up. This means our footing dimensions have no issues. We can now see that the soil pressure is almost uniform in service load level. Check the overlay shear diagram option to see the internal shear forces being experienced by the footing. We can also do the same for the moment diagram. Scroll down the page to display more details about the analysis results. We can see here a clear plot of the shear and moment diagram of the selected loading combination. Also, there is a plot of the shear and moment envelope. This is very important when we are dealing with multiple load cases and combinations. This gives us the range of the maximum and minimum values of the shears and moments under all possible loading combinations at any location within the footing length. There is also tabulated results of the analysis which you can review. You may export this table in a new Excel worksheet if you need them. Tabulated results for punching shear. Tabulated results for one-way or wide beam shear. On the lowest part of the page, we can see auto-generated reinforcement detail of the footing. Finally, we can see the detailed calculation if we click on the Display Calculation button. The calculation was made in pattern to our handwritten calculations, so we could understand it better. We can export this calculation as MS Word document. Here you can edit the calculation to suit your needs. Design example 2. Using the same problem, design the foundation using a strap beam. Use a rigid strap beam with 500 mm width and 800 mm depth. Back to the CSF program. Set the footing type to strap footing. We can assume a smaller footing thickness now that punching shear is not likely to occur. Let's assume a 300 mm footing thickness. Strap beam width is 500 mm, and the depth is 800 mm. Assume a 2.5 by 2.5 meters footing for each column. Click OK to save the new inputs. Modify the strap beam reinforcement to suit your desired parameters. Now that the new footing is ready, we can now perform the analysis. Warning messages popped up. The program says the allowable soil pressure exceeded. This means we need to increase our footing size. Also, the footing fails in one-way shear. Our assumed thickness is a bit short. We go back to our inputs to make the necessary adjustments. Increase the footing size to 350 mm. Increase both footing to 3 by 3 meters. Click OK to save the adjustments. Let's run the analysis again. No warning messages popped up. This means the thickness and size is now adequate. Take time to inspect the results to build your own engineering judgment. Footing details of reinforcement is shown down below the page. Take note that these drawings have been generated from information that is based only on calculated strength requirements, and are also a representation of the design output in an schematic form and are not for construction. All details should be reviewed for compliance with local detailing codes and other requirements. Finally, we can click on the Display Calculation button to review the analysis results and design calculations. Now, the design of combined and strap footing were made easy. Thank you for watching.